Lesson 5.3 deals with binomial probability distributions. The requirements for a binomial probability distribution are that the procedure has to have a fixed number of trials. The trials must be independent, meaning that the outcome of an individual trial doesn't affect the probabilities in the other trials. Also, it's a binomial probability distribution when each trial has just two outcomes. These outcomes are usually classified as either a success or failure. Also, the probability of a success must remain the same in all trials. Let's talk about the independence requirement. We can treat dependent events as independent events if it meets the qualifications for the 5% guideline for cumbersome calculations. This guideline says that if the calculations are extremely cumbersome and if the sample size is no more than 5% of the size of the population, we can treat the selections as being independent, even though the selections are made without replacement. So we get to apply this guideline for situations where maybe the probability we have to keep changing it with each selection because we are making the selection without replacement. So that would affect your totals for each fraction or each probability. And let's say that you have 100 different events taking place or 100 different selections where you have to keep changing your denominator. And that would be a very cumbersome calculation to do by hand. So as long as the sample size is not more than 5% of the size of the population, we can go ahead and act like all of the probabilities are the same or that it's an independent event. Here's some notation. First, n is the number of trials, x is the number of successes in n trials, p is the probability of a success in any one of the trials, q is the complement of p. It's the probability of a failure in any one of the trials. P of x is the probability of getting exactly x successes out of n trials. Let's look at some examples of binomial distributions. Here we want to determine if the given procedure is a binomial distribution or not. If we survey 12 jurors and record whether there is a no response when they are asked if they've ever been convicted of a felony. Well, in this case, since their response or their outcome would be either yes or no, that would qualify as being binomial. What if we treat 50 smokers with Nicorette and record whether there is a yes response when they are asked if they experience any mouth or throat soreness? Because the outcome is either yes or no, this would qualify as a binomial distribution. What if we record the number of children in 250 families? Well, the number of children varies. You could vary from 0 children, 1 child, 2 children. So there's not just two outcomes that we can record for this event, so this is not binomial. Here we want to determine if the given procedure results in a binomial distribution again. 15 different governors are randomly selected from the 50 governors currently in office, and the sex of each governor is recorded. Now you might think that this is binomial because when you record these, you would either say male or female, which is two outcomes. However, 15 out of 50 governors is 0.30, and this does not satisfy the 5% rule of classifying this as an independent selection. You see, when we select the governors, we select them without replacement when we record their gender. So you have to make sure that it follows the 5% rule, and this one does not. This is the formula we use to calculate a binomial probability. It's P of x equals NCx times P to the x times Q to the n minus x. Remember that n is your total trials that are conducted, and x is the number of successes you're trying to get. P is the probability of a success, Q is the probability of a failure. NCx is another formula involving factorials that you can find in your textbook, but I'm going to show you how to enter it in to your calculators to compute that value. It is a combination. In your textbook, we also will sometimes use table A1 on page 749. This table gives us certain probability answers as long as the probability for our problem is one of the values in the table, like 1%, 5%, 10%, 20%, and so on. If the given probability is not in the table, then you have to use the probability formula to derive your answer. Here we're going to practice using table A1 to find the probability of X successes given the probability P of a success on a given trial. So we're told that N equals 4, X equals 3, and P equals 0.30. So we have 4 trials. We're trying to find the probability of getting 3 successes out of 4 trials, and the probability of a success for a single trial is 30% or 0.3. So looking this up in table A1, we go to the 0.30 probability row and line that up, and then look at N equals 4, slide over to X equals 3, and then you get underneath the probability that you want, and you should have your answer from the table as 0.076. You can also derive that answer using the probability formula on the previous slide. Here we're going to look at an example of calculating the probability for a binomial distribution using the formula. So we have N equals 6, X equals 4, and P equals 0.75. Table A1 is not helpful because it does not include this specific probability. Here is our formula for finding the probability for a binomial distribution. So plugging in our values, we get P of 4, meaning the probability of getting 4 successes out of 6 total trials is equal to 6 combination 4 times 0.75 to the 4th power times 0.25 to the 6 minus 4th power. So in your calculator, if you have a Texas Instruments calculator, you would type 6, and then the PRB button is where you will find this combination formula, and you arrow over to NCR and hit enter. The screen now says 6 NCR, and then you finish out your entry, and it should look like this when you type it into your calculator. 6 NCR4 parentheses 0.75 to the 4th parentheses 0.25 to the parentheses 6 minus 4 is 0.2966. You can also click on the video tutorial to watch this process demonstrated. Here we want to use this table to find the probability that at most 2 subjects experiences headaches. And then we want to determine, is it unusual to have at most 2 of 6 subjects experience headaches? So this table shows that N equals 6 and P, the probability of a success or of getting a headache is 0.167000. So the probability of at most 2 can be reworded as P of less than or equal to 2. And so I'm looking at the x's, and I'm looking for all x's where it's either 0 or 1 or 2. And we get our probabilities that have already been calculated for us. It's in the table. Remember that OR means to add your separate probabilities. So from the table I see that the probability of 0 headaches is 0.3341, the probability of 1 headache is 0.4019, and the probability of 2 headaches is 0.2014. The sum is 0.9374. So there's about a 93.74% chance of getting at most 2 of 6 subjects experiencing headaches. An unusual probability is a number less than or equal to 0.05 or 5%. Since 0.9374 is not smaller than 5%, it's not unusual for at most 2 subjects to experience headaches. The Hemingway Financial Company prepares tax returns for individuals. According to the IRS, individuals making $25,000 to $50,000 are audited at a rate of 1%. The Hemingway Company prepares 5 tax returns for individuals in that tax bracket, and 3 of them are audited. We want to first find the probability that when 5 people making $25,000 to $50,000 are randomly selected, that exactly 3 of them are audited. So this is a binomial distribution because we have the outcome could be they are audited or they are not audited. And so our n is 5 because we have 5 total tax returns. P is 0.01 because that is the probability that you will be audited. So that's considered to be a success, even though we wouldn't think it is. So 0.01 is the probability of getting audited. X equals 3 because that's what we're trying to determine. What's the chances of having 3 audits out of 5 tax returns? So we can use table A1 because 0.01 is a common probability in that table. So P of 3 from that table is 0 plus, meaning pretty much a 0% chance that this would happen randomly. Now let's continue and find the probability that at least 3 people are audited. So we're changing the wording a little bit. At least indicates less than or equal to 3. So we still have n equals 5 and p equals 0.01, but we have more than one x that we need to determine. Probability of at least 3 would be p of 3 or 4 or 5. Or means to add. So we have to find these individual probabilities from our table and find their sum. So I'm going to look up n equals 5, x equals 3, and line it up under the 0.01 probability. And then I do the same thing for n equals 5, x equals 4, and then I do it again for n equals 5 and x equals 5. The sum of these probabilities is also 0. So the probability of getting at least 3 people audited out of 5 tax returns is 0. Based on the preceding results, what can we conclude about Hemingway customers? Are they just unlucky or are they being targeted for audits? Well, since we found that the probability of the IRS randomly selecting 3 of 5 tax returns for audit is very, very low, almost 0%, we can assume that the individuals were being targeted for audits. When someone buys a ticket for an airline flight, there is a 0.0995 probability that the person will not show up for the flight. An agent for Air America wants to book 24 persons on an airplane that can seat only 22. If 24 persons are booked, find the probability that not enough seats will be available. Is this probability low enough so that overbooking is not a real concern? So let's let x equal the number of booked passengers that show up for the flight. We know that the total people is 24, so that's n. The probability that a person will show up is 1 minus the probability that they don't show up, 0.0995, giving us 0.9005, or about a 90% chance that the person will arrive. The probability that there will not be enough seats would occur if finding the probability that we have 23 people show up or 24 people show up. So this is because of the limit of seats on the flight, and if we go over that limit there's not enough seats. So we need to focus on 23 or 24. So that's going to be our x's. X equals the number of booked passengers that show up. So if x equals 23 we are overbooked, and if x equals 24 we are overbooked. We need to find these individual probabilities and then find their sum. So I need to use the probability formula because my probability P that I'm using is 0.9005, and that is not a probability that's found in table A1. So P of x equals 23 is 24C23 times 0.9005 to the 23rd power times 0.0995 to the first power. So remember that that second value is the Q. And that's going to be the complement of the P. So you subtract one of the values from 1 to get the second number. This simplifies to 0.2144. Now for x equals 24, we have 24C24 times 0.9005 to the 24th times 0.0995 to the 0 power. Anything to the 0 power becomes the number 1. So this equals 0.0808. Now we find the sum of these probabilities and we get 0.295 as the answer. So since 0.295 is about 30% and that's greater than 5%, then such an event is not unusual. So the probability is high enough that overbooking is a real concern.